Okay, in Chapter 3, our authors broached the topic of differentiation, and they first start out talking about average rate of change. So this is the only topic in this section that does not require differentiation. And you don't yet know what differentiation really is in terms of this course. So we're going to start out talking about average rates of change, and then eventually we'll come back and compare average rate of change to instantaneous rate of change. Okay, so starting out, the average rate of change. The definition of average rate of change I've written down below, and you can see that it's just the definition of slope. So in terms of just application, if you're given 2 points, so let's say we're given the points 2, 5, and -3, 4, let's go ahead and find that slope, because that slope is just your average rate of change. Okay, so following the formula, the f's are the y's, and the f of b, f of a of y values, and the b minus a are the x values. So looking at our work, I would have 5 minus 4 over 5 minus a -3, which makes it 5 plus 3. So that's going to give me a slope. Let me see, hold on a second. Did I lose my head? 5 minus 4. Oh yeah, hold on. Let me back up a little bit. Okay, so what are my y values? I started with the 5. I'm going to start with the 2. So 2 minus a -3, so that's 2 plus 3. So I have 1 over 5 is my slope. It's a positive slope. So what I'm going to do right now is I'm going to show you the form of a line that we will use most often in calculus, and that is y minus y1 equals m times x minus x1. So once you have your slope, can you give me an equation of that line connecting those 2 points? So what you would do is you have 2 options. So you could say y minus y1, we can use these points first. So that would be y minus 4 equals 1/5 times x plus 3, because it got flipped due to the negative. So that's one expression for that line. A second expression, if I use the first point, will be y minus 5 equals 1/5 times x minus 2. Now the nice thing about this is that these are both the exact same lines. So that's kind of a fun exercise for your kiddos to show that you can write equations of lines and they actually look different. So if you convert this into the y equals mx plus b form, you'll see that they're the same line, and I'll leave that for you if you want to prove that to yourself. But more importantly, this form of a line is what we're going to use throughout this course from this point forward, unless we're instructed to use a different form. But this is the point slope form. So here's your points, here's your slope, and it is the easiest form of a line to get because you don't have to calculate the b, and you just put in your point that you have and your slope, and you are done. Okay, other things that other extensions that our textbook has for the average rate of change, they talk about, you can talk about the average heart rate, and this is all good discussions because you have to convert your units sometimes. So maybe you are calculating a number of beats per second, but you need to record it per minute, so you need to know how to do dimensional analysis to convert them. So that's just something, a nice little application of this section. And just to quickly finish this topic, so in terms of average rate of change, painting rate was an example they used, walking, another example. Here again, you may need to be converting units, so it's a good practice for this section as we get ready to delve into more of the calculus. Okay, I've taken this graphical example from page 117 because I think it's terrific, and I put in some additional notation on it. So what they don't tell you is that we tend to, in calculus, the line that hits your curve in 2 places that are nearby is the secant line. The secant line measures average rate of change. If you decrease the change in x, so see this change of x right here? As you decrease it, what's going to happen to this line? Well, if you decrease it to this, so this point right here, say, as I go up, okay, that's my new b, then my secant line is going to go through that point and that point. So see, it's getting a little bit steeper. As I continue to decrease my distance, and as that distance, the change in x, as the change in x approaches 0, what's happening to my line? So let me just erase this little thing here, and let's look at the resultant line as x goes to 0. Okay, the resultant line, I'm going to change the color, I guess. Change that. Is going to be the line that's going through this point. Okay, as the change in x gets closer and closer to 0, I am changing my line from a secant line to a tangent line. Tangent line. Okay, tangent lines measure instantaneous rate of change. Secant lines measure average rate of change. We're going to move our discussion to measuring tangent lines, because now we're going to measure the slope of a curve using calculus. Okay, you don't usually talk about the slope of a curve in pre-calculus levels. Okay, if you think about slope, you're thinking about a line. Well, what's going to happen is the slope of this tangent line is going to approximate the slope of the curve at that point A. So that's where we're going with this discussion. Before we get into the calculus of things, we're going to talk about average rate of change and make sure that you can calculate that over an interval. So, problem 1 and 2, they give you intervals that are graphically represented, but they also give you the equation. So what I would tell you to do is put that equation into your y1, and then you can use your table or use your graph and then find the value of the point so that you get your y values. So for example, when I did that, my f of -2 was 1, and my f of -7/4 was 0.3125. So when I did my first problem and I wanted to find the rate of change, so change in y over change in x, I'm getting 1 minus 0.3125 over -2 minus a minus, so plus 7/4, and my rate of change for this problem ended up being -2.75. Okay, make sure you can do that, and we'll do number 2 on the next page. Okay, here's our next problem. Okay, so it's a rational function, so we can see it's nicely graphed there, and we can talk about limits with this if we wanted to. So we know that the limit as x approaches +3 is going to be undefined because it does not exist. So this is not a continuous function. And because it's not continuous, when we get to derivatives, I can't take the derivative at x equals 3 because it's not differentiable there. But that's a conversation for another day. So what I would do, I would urge you to put your f of x function in your y1 and get your y values using either the table or your graph itself and asking for the value of both of the the x values that they're giving us. So when I did that, I got 1/5 for f of -2, and for f of -3/2, I got -0.2, and it's bar notation. Okay, so when I got the slope, I'm going to say go ahead and I guess round this to the nearest hundredth, and so I'm going to make that 0.22. So my change in y over change in x ended up being a negative 0.04, and that also had bar notation. So if you can just check that you can get that, that would be awesome. So we're going to do 2 more of these problems, I believe, on the next page. Okay, assuming that you are following along with this, I will tell you what I got for my answer. So my average rate of change for number 3 ended up being a positive 5.25. Again, I'm using my calculator to get my values. And for number 4, I'm getting a negative 5.3 with bar notation. Okay, so that ends the average rate of change problems. So the key thing is to remember that you're taking the slope of basically a secant line, so you're going to hit your graph in 2 places. Now we're going to talk about instantaneous rates of change, and that is the slope of a tangent line, as we're going to come to learn. So I typed up some things here. So I'm saying when discussing average rate of change, we describe it as being the slope of the line connecting the 2 points within our interval of analysis. All right, so that is a secant line. If our function is a line, then the average rate of change is just the slope of the line. So for example, if your function was this line, y equals negative 3x plus 10, the rate of change is always going to be negative 3. That's the slope of a line. Okay, where this changes is if you have a slope of a function that is not a line, and you want to know what's the rate of change, say between here and here, and really you're looking at part of a parabola. Now you're going to be drawing a line between those 2 points that does not land on top of the original function, and you're going to be telling me about how the function is changing between that interval. Okay, so as I go on reading here, if our function is not a line, then the average rate of change will depend on your interval. And this is a very, very important point. So for example, for this function that I've drawn over here, if I'm going to check this interval, I have 1 rate of change. If I'm going to check this interval, however, I have a different rate of change. Whereas for the line, no matter where I check it, I will always have the exact same rate of change. All right, because it's just a line, and the rate of change will always be the slope, and the slope of a line is constant. Okay, so in order to understand the behavior of a given function, one must understand how the function changes at every point. And that change is your instantaneous rate of change, and that's where the calculus comes in. Okay, so let's go on to the next slide. All right, so our textbook uses a car as an example to illustrate the difference between the average rate of change and the instantaneous rate of change. So if you drive 100 miles in 2 hours, your average rate of change in y over change in x, is 50 miles per hour. Okay, so that's your average rate of change. If, however, during your trip, you look at your speedometer and it's at 70 miles per hour, that is your instantaneous rate of change at that instant. Okay, I've done this graphical representation. I pulled it from the textbook on page 119, and it's showing us that if we draw a tangent line to this particular function at 5 different points, we get 5 different results. So you can tell how that is giving us a good idea about how this function is changing. Notice that each of those curves, each of those lines that are drawn to the curve, hits it in only one place. Those are tangent lines. Tangent lines measure instantaneous rate of change. So notice that P1 is a positive, P2 is a positive, P3 is even more positive, it's the steepest. Then P4 is also steep, but steep in a negative fashion. P3 is back to being positive, but yet not as steep as P3, almost parallel, I would say, to P1. So you can have a lot of observations about your graph by using tangent lines. Okay, let's go on to the next page. Our textbook only discusses the problem of getting a tangent line at a corner situation. So that means right here. This is what our textbook discusses. But there are actually 4 different scenarios where even though a function is continuous, and we've talked about that in the previous chapter, function is continuous if you can sketch it without picking up your pencil. So even though it's continuous, you may not be able to do a tangent line throughout the entire function. So where does that happen? If you think about a tangent line as really being the limit as from the left and from the right, as the difference goes to 0, you're going to see that having a sharp point prevents drawing a tangent line where x equals a. Having what they call a cusp prevents it at x equals a. Here's the corner discussed in our textbook, and here's the 4th type of issue that prevents you from drawing a tangent line, and that's if you have a vertical section of your graph. Okay, so those are all things that will not allow you to get the slope at that particular point. It's only a problem at A. Outside of A, so to the left and right of A, it's not a problem. But at A, you cannot draw a tangent line. Okay, so if we can determine the slope of a tangent line drawn to the function at some point A, then we know that that function is continuous and differentiable. So continuous is a requirement for being differentiable, but it's not the be-all and end-all. In order to draw a tangent line, your function has to be at a minimum continuous. You also have to have it be differentiable at that point. So it has to be, it's a twofold test. Continuity gets you in the first door, differentiability gets you in the second door, and then you can take your tangent line. So this is very important terminology. Now, how do we determine the slope of a function at a given point? We use the difference quotient, okay, and they take the limit as h, which is the difference between x1 and x2, as that approaches 0. And then we evaluate the limit at the x value specified. Okay, so that sounds absolutely awful, but we are going to keep it simple. We're only going to deal with quadratic functions, okay? So just quadratics. This involves a lot of algebra, but as long as you're systematic, you'll be terrific at this. Okay, so here we go. So what is this difference quotient of which I speak? This is it, okay? This is your expression for a difference quotient. So here is your expression for slope. We're going to call it f prime of x. It's basically a derivative. Okay, so this is how we're going to determine derivative until we know some of the easier rules. Okay, so this is your basic structure. So the difference quotient is this, and in order to calculate, I'm going to go through these steps. So this is what it is in theory. First, calculate this quotient. So this is f of x2, so f of x2 minus f of x1 equals, this is x2, this is x2, and this is x1. So you're basically just doing y2 minus minus y1 over x2 minus x1. Okay, that's your underlying premise of what you're doing. So then what's going to happen is this difference between the x1 and the x2 we're going to term as h. As h goes to 0, and just like I spoke about in our first time we had a slide like this, as this h goes to 0, we are moving from a secant line to a tangent line. And that tangent line is my instantaneous slope. Okay, or instantaneous rate of change. Okay, so we're going to practice this on the next slide. It's going to take a lot of practice because, as I said, it's a lot of algebra, and there's some very simple things that you can do incorrectly when doing this. Things like distributing a negative, hugely important. So we're going to practice this extensively. All right, so we're going to practice with this quadratic function right here. So f of x equals 2x squared plus 7x. So I want to find f prime of x, which is the instantaneous rate of change. Okay, so here is my expression that I need to keep in mind. This f prime of x equals the limit as h goes to 0 of y2 minus y1 over x2 minus x1 is what's happening. So this is f of x plus h minus f of x, which was the original function, over the difference in the x's. So x plus h minus x. All right, so that's your format. How do I apply that to the function that I have? Because the first thing I just wrote down is just generic. So let's begin. So f prime of x, and your notation is really important, even with a cursor, even with this little stylus. Okay, it's going to be the limit, you've got to write this every time, of x minus 0, and I'm going to put in my f of x function, but I'm going to plug in an x plus h wherever I have an x. So this is what I'm writing. 2 times, so I have x plus h. Okay, I think I'm going to have to change the stylus here. Squared. Okay, let me just get this set up first. Okay, so it's 2 times x plus h squared plus 7 times x plus h, and then minus, I'm going to use my bracket, 2x squared plus 7x. Okay, all over x plus h minus x. All right, so now, do you see what I have? So let me just do some circling in red. This is this. Okay, and then this piece is this. And then I just have change in x in the bottom. Because remember, the difference between these two things, or these two x values, is the variable h, which we want to go to 0. Okay, so let me continue. So let me get back my color. That was that. Okay, so next thing. I'm going to have to expand everything in the red box. So f prime of x equals the limit as h goes to 0 of. So I'm going to FOIL the h, x plus h, all right, and I'm going to multiply the whole thing by 2. So I'm going to skip steps here just to conserve space. So when I do that, I end up getting 2x squared plus 4xh, and then plus 2h squared. All right, so that's the whole first piece. Then I'm going to also get 7x plus 7h. That's all the red. Okay, so then I'm going to subtract away 2x squared, watch this, minus 7x. That's going to be very, very important that you don't forget to distribute that negative. In the denominator, can we just cancel out the x's because they're opposite signs? And that will leave me with a simpler plain old h in the denominator. Okay, so now what has to happen for this to all work out you have to make sure that your math allows you to cancel out every x not associated with an h. So watch what I mean. Looking only at the numerator, I have a 2x squared here. It has no h. I'm going to look. Do I have its opposite down here? And yes, I do. I have a positive 7x here. I have a negative 7x here. That's good. If something does not cancel and you're left with an x without an h, don't go forward. Go back and figure out where you may have made a mathematical error and fix it. Okay, so I'm going to copy this slide to the next page and then continue the process. Okay, so let's continue working with this. I'm going to rewrite it again, eliminating the items that I have been able to cross out. So in the numerator, I have 4xh plus 2h squared plus 7h, all over h. So next step, factor out that h. So just to step back for 1 second. Remember taking limits. You would just plug in the 0 as a test. If you plugged in the 0 right now, what would happen? Well, this goes to 0, and then your whole thing is undefined. So that's why we're trying to eliminate, all the stuff I'm doing right now is trying to eliminate the h from the denominator. Once you have it eliminated, then, and only then, do you actually take the limit, which means plugging in the 0 for the h. Okay, so continuing to try to eliminate, I'm going to factor out an h from the top. So I get 4x plus 2h plus 7, and then I still have the h in the denominator. At this point, notice what happens to those h's. These h's can cancel because it's just a 1, and I no longer need it. So now at this point, and only at this point, do I take the limit. So I'm going to plug in the 0. Once I plug in the 0, I don't need to write the limit as h goes to 0. So I'm going to actually see that I get 4x plus 7. Why is that the case? Because once I let this h go to 0, that term fell away. So this is an equation for my slope of the tangent line. Okay? This is the equation of the slope of a tangent line drawn to any part of our original function. If I want to know what the slope is at a particular number, I would plug it in. Alright, so, and then we're going to do that for our next little section. So this is going to be my slope, 4x plus 7. So let's look at the next slide, and we'll use that 4x plus 7. Alright, so now it says, now find the slope of the tangent line drawn to fx equals 2x squared plus 7x. So we found the generic slope is this, but now they want us to find it at certain values of x. So if I want to figure out what f prime of negative 3 is, I'm going to plug in negative 3 wherever I have an x. Okay, so that's going to be negative 12 plus 7, that's going to equal positive 5. Okay, continue that. F prime of negative 1. Wherever I have an x, I plug in a negative 1. So that's going to be negative 4 plus 7, that's a positive 3. If I want to figure out what the slope is when x is 0, 4 times 0 plus 7, that's going to be 7. And I can continue. If I plug in a 3 here, I will get a 19. If I plug in a 1, I will get an 11. So this is how you are figuring out what the slope is exactly at different x values. So your slope of the tangent line drawn to your function is very dependent on where you draw that line. And so it's dependent on which x you choose. So that's the big takeaway from this problem. Okay, so now we have the slope. So can you find the equation of the tangent line drawn to, so this should say of the tangent line drawn to this function at these various values. So let's just use a couple of them. If x equals 3, and I know that the equation of a tangent line is easily determined by using point-slope form, then what I'm going to do is I know at -3 the slope was 5. -3 flips that to 3. I need to figure out what y1 is, so I'm going to take my y of -3 and plug it back in this original function up there, and I get a let's see what I get. Hold on a second. Well, let's do it on the calculator and I'll come back to you. So that y value is actually a -3, so that's going to flip this. So you should be able to create all of these lines. So let's do one more. What if x is 1? So if x is 1, I had said that our slope was 11. So if x is 1, then the equation of the tangent line drawn to that point will be y minus 9 equals 11 times x minus 1. And just make sure that you can get that yourself. Okay, I put this graph in here because it's going to help you understand about drawing these tangent lines. So let's pick a couple of points. So what if I say I want one point right here, and I draw a tangent line to that point? That tangent line is going to be positive. It's going to have a positive slope. What about if I take -1? That tangent line will be 0. This is 0 also. This is very steep. This is 0 at this point. This is very steep going negatively. So I have a positive slope, a 0. In here would be a negative slope, another 0, a positive, a 0, a negative slope. So you can see that if you know the slopes of these tangent lines drawn to the curve, you can kind of sketch out your curve to a certain extent. And that's the beauty of calculus. It'll give you insight to your functions by analyzing these functions at various points going from left to right. You should be able to identify slopes as being very positive, negative, very negative, or 0. So that's your test for yourself to be able to do that. Okay, so I want to at this point introduce the concept of drawing a function. Okay, so that's the function, and drawing the equation of a tangent line drawn to that function at every point on the same graph. Okay, so the red is the slope of the black. So let's kind of check that. Okay, the easiest place, I'm going to change color so you can see what I'm doing. The easiest place to check that is right here. So tell me, what do you think the slope of the original function is just a little bit less, when x is just a little bit less than -2? Well, it looks like it is a flat line. That slope is 0. And look, that's exactly where the value is of the equation of the tangent line. So this value is 0. So you read the slope of the function off of the y-axis when you look at the derivative of the function. Okay, so we're going to relax about that and not get too stressed about the terminology. I want you just to get a flavor of it. So let's pick another point. So I'll go a different color, and let's see, what about this point right here? So if I want to know what is the slope of a tangent line drawn to that curve, because that also gives me what's the slope of the curve, right? So here's the tangent line. That's a little bit to the right of -4. So say that's -3.5. Go down to your tangent, your first derivative, and read the slope. When I look at it, I know it's negative. So look, when you read it off this curve, aren't you reading negative values? So your first derivative, that's what this is your first derivative, that gives you the slope of your function at every point. So let's keep going. We'll do one more. So changing to this pinkish color, what if I want to figure out what is the slope of my original function when my function is up all the way up here? So I draw my tangent line. Gosh, I see it's very steep in a positive way. So go down from that x value, hit your first derivative, and read over. And sure enough, your slope is about positive 15. That's very, very steep. Down here at the -4, when I read across, my slope was about -5. All right, so hopefully you're getting the sense that you can use that first derivative to give yourself the value of the slope of your tangent, of your original function at various points along it. Okay, that's a very, very important concept. Okay, we're going to start talking about 3.3, motion and derivatives, on the next page. Okay, on this page, they're talking about the path of a rocket. So Adrian's rocket is projected upward, and its path follows this function. So by looking at the function, I know that the rocket starts at time 0 right on the ground, and it goes up and comes down in accordance with gravity, and it hits the ground right here. Okay, that's when it is 0 height off the ground. So this is your height. I should have my axes labeled, and this is my time. So the height is a function of the time the rocket is in the air. All right, note that all this action is only happening in the first quadrant, and that makes perfect sense. We can't have negative time, and also the rocket's not hitting the ground and then going below the ground. All right, so we're all dealing in the first quadrant. So let's go through these first 4 questions, because we can answer these without using our calculus. And sometimes when I'm teaching my calculus class, my kiddos forget that they have the skills with their Algebra 2, and to some extent with their Algebra 1, to already be able to answer these questions without delving into the calculus. So looking at our graph, at what time does the rocket leave the ground? So it's leaving the ground at time equals 0 seconds. Okay, because I'm just seeing that this is where it's starting to go up. At what time does the rocket return to the ground? So it hits the ground right here, and this is time of 8 seconds. And you should be using units for these. When is the rocket at its highest point? So that's right here, and I want to know when. So I need the x value. Now in this situation, we can pretty much read it off the graph, but don't forget that you can get your vertex. Okay, this is a vertex back from Algebra 2, and that vertex is -b/2a, comma, the function evaluated at -b/2a. That gives you the x and the y. So if they're asking you for the x only, what you would do is you would say -b, so that's -128 over over 2a. So 2a is going to be -32. Okay, so my answer would be at time 4 seconds. So 4 seconds. So even though you think you can read it off, what if it was like 4.1 seconds? You really couldn't determine that. So it's always best to use your formula or use your calculator to get your vertex. Don't assume that what you're reading is exactly it, unless they say, using only the graph, tell us what the height is and what time does that happen. Then you can be using your graph. Okay, what is the highest height? So here I cannot read it directly because I know it's above 250, but I can't really tell how far above. So what you would do is you would evaluate your function at 4 seconds. So you're going to take your h of 4, plug it in and solve, and you should be getting 256, and I believe all my units are in feet. Yes, they are. Okay, they're all in feet. So that's what I'm getting there. All right, now we're going to try to figure out the slope of this curve. So I want the generic slope using the difference quotient. So that's going to come next, and that's going to be more algebra. So we'll do that on the next slide. Okay, so I started writing this out. Okay, the first thing I did for us was to put the original function right here, and I'll put it in this little red box. You can see it's not part of my problem. So now I'm going to try to take the limit as h goes to 0 of y plus h, right? So of this whole difference quotient. So here is your difference quotient, and you can see that I've added an h wherever I had just a plain old t. Oh, and I have to do one more thing, so hold on. So let me fix this, because this should have had a t plus h. So let me just erase this right here, and let me do a plus h minus, and then that's going to be in parentheses. Okay, so that's better. So, and I've got to do that down here too. So let me fix this up, and I'll turn it back on in just a sec. Okay, all fixed. So I am now going to FOIL this piece, and here it is right here. So be careful about the negative out front here, because that's going to impact what we're doing as well. I expanded this piece right down here, and now I very carefully distributed the negative, although clearly not carefully enough, because this needs to be a negative right there. Alright, so then, and then I finally also canceled out these t's because they're opposite signs. Well, they should have been opposite signs. Right, so now they are opposite signs. Alright, so we're back in shape here. Okay, so now next step, I'm going to distribute the negative 16 to all the pieces inside. And I'm going to write it over again, so I'll turn it off for a second, and then when I turn back on, you'll be able to see it. Okay, here's our next step. Everything is expanded. So now what I want to do is cancel out in our numerator, and what should happen is any term that does not have an h attached to it should cancel. If it doesn't, we'll go back up and see what we did algebraically incorrectly. So here's a negative 16t squared, here's a positive 16t squared. Here is a negative or positive 128t, here's its counterpart, negative 128t. Okay, everything else I see that's remaining has an h attached to it. So next step, factor out your h. So we'll do this together. So I'm going to write this one more time. F prime of x equals the limit as h goes to 0. Factor out your h. I get negative 32t minus 16h plus 128. Okay? And then that's all divided by the h. So because it's divided by the h in the numerator and the denominator, I'm going to cancel those out. And now let's go ahead and take the limit. So I'm going to say equals over here. So equals, and take your limit, which means put your 0 in here. This term falls away, and my limit ends up being negative 32t plus 128. So what is that? That is f prime of x. So that is the generic equation of any tangent line drawn to our Adrian rocket graph. So we're going to use this in the next slide to determine the velocity at different points. Okay, so I should say one word about the word velocity. So if you are given a position function, and that rocket equation was a position function because that tells us the position at every t value. The first derivative of a position function is velocity. Okay, that is very critically important. They're not going to tell you that again. So they might give you a position function and say find the velocity, and you need to know to take the first derivative. Likewise, as we look ahead, if they give you a position function and they say find the acceleration, that is your second derivative. So you will go through this whole process again and find the second derivative, which we will do in a second. But for right now, let's evaluate the velocity of your function at the different times. So if you have time of 2, you would plug in 2 in your velocity function, and you should get 64. And at this point, you're going to report your units. It is feet per second. That's a velocity measurement. Okay, if we had f prime of 3, then when I plugged it in, I should be getting 32 feet per second, and just go ahead and try that. Okay, let's go back for a second and look at our rocket. So if I say that f of 2 is 64, does that kind of make sense? Here is where that is, and it's going to be positive, and it looks, pretty positive, so I think 64 is a reasonable answer. I could extend this line, this tangent line, and approximate the slope of it, and my guess is I would get, pretty close to 64. Okay, what do you think about the pink line? That's at 4 seconds. What do you think that slope's going to be? If you look at it, it should be 0, correct? So let's go back to our current slide, and if I say, what is f of 4, when I plug it in, I'm going to get negative 32 times 4, which is negative 128 plus 28 plus 128, so I will indeed get 0 feet per second. So that's a good thing to notice. So at the max, when your rocket gets at its maximum point, what is the velocity exactly there? Well, that velocity is 0 feet per second, which is interesting. Think about when you ride a roller coaster. You know how when you get to the top of a roller coaster, you kind of feel like you hang for a second? Your velocity there is 0 feet per second. So it all kinds of makes sense. So calculus is a very valuable math for that reason. It gives you very good insight into what you experience in daily life. Okay, in the last slide, I'm going to show you how to do the acceleration problem, and then we'll be done with these with this video. Okay, I got us started here. So, and I kind of changed from H to F, so I should have been more consistent. The original function I gave you of Adrian's rocket was an H function, so we should keep it as an H prime function when we take the derivative. So I hope that didn't confuse you. So now if I want to take the second derivative, I'm actually looking for, and here's some new notation for us, H prime prime. And I told you already that the second derivative of the position function is acceleration. You can also term it as the derivative of the velocity function. Okay, so using limits, I'm going to take the limit as h goes to 0, not of h of t at this point, but as h prime of t, because I'm taking the derivative of the velocity. So we'll use the same procedure. I'm going to add h to the first part, and then subtract away the original function all over t plus h minus t. Remember, you're just trying to get the generic slope equation. So right away, we can cancel the opposite t's so that they're out of our way. And now let me change back to my green, and we'll continue. So I'm going to distribute that negative 32. So I'm going to write this line again. So maybe I will just set that up for you and then turn this back on. All right, so here's our second line. So I've just distributed the negative 32 to both the t and the h, added the 128, and then distributed the negative to both the negative 32t and the positive 128. So this is the expression I get. So at this point, what we're going to do is wherever I have a t that doesn't, or have a variable that doesn't have an h attached to it but has a t attached to it, they should cancel. So does that happen? Well, here's a negative 32t and a positive 32t. So yes, they go. And here is another term without an h attached, a positive 128, and yes, I do have its negative function, negative 128, and they cancel. So what am I left with? Let me turn back to my green. And what I'm left with is the following: h prime prime of t as the limit of h prime of t as h approaches 0, and that's going to equal, I'm going to factor out my h's now, and all I have is a negative 32 up top. So what's happening here is that everything else is going to cancel, and my acceleration, so hold on, my acceleration, which is now my h prime prime of t, the second derivative, is just negative 32, and I was in feet, so feet per second. So what's interesting about this? What I find interesting is that your acceleration is a constant. So it's not time dependent. There is no t associated with it. So therefore, regardless of where we are on that Adrian rocket curve, our acceleration is always negative 32 feet per second, even though our velocity is always changing. So that should be an interesting little takeaway. Okay, well that ends our notes. So I will post some problems for you to practice on Joule.